Okay. Good morning, everybody. Welcome to this GNF panel. My name is Gerd Gruppe. I'm a member of the board of DLR, and they're responsible for all the agency affairs. And I'm pleased to see you here all. And we want to talk about science, innovation, about pushing boundaries, and of course, a little bit about Made in Germany. The panel, the headline of this panel is Pushing the Boundaries of Research. What does it mean? In our opinion is what we try in Germany to support is the better use of space science results. We try to support young companies, we try to support young people to run their own business, but we are fully aware that the basis for this all is science. And science means the linkage between basic science, applied sciences, and innovation and development in the companies. So we try to show the whole range of these activities on this panel, and what a seamless chain from basic research to high-tech products. We will meet here on the stage four distinguished panelists, which will tell you about these subjects, about basic science and innovation. First of all, I would like to introduce to you Professor Marc Avila, the second here on the row, from the right-hand side. He's from the Center of Applied Sciences in Technology and Microgravity in Bremen. Dr. Jens Große from the University of Bremen. And Matthias Motzigemba from the TESAT company in southern Germany. And my colleague from DLR, Professor Stefan Ola Metz. In our opinion, science is not only, is in the first way, a major driver for the space age, and we distinguish three types of space activities. The first is space science from space. The second is science in space, like microgravity research and something like this, and science of space, like astronomy and planetary exploration. Our job as a space agency is to meet, to help, to contribute to solutions to the big challenges of today. And in contrast to some opinions, the problems are getting more complex, and so our answers have to be more complex as well, more performant, more reliable, and maybe more orientated to products. And so that's the reason why we try to push applications in the forefront. I would like to give the floor to the panel and to the speakers. And after that, you have the possibility to ask questions. There will be the young ladies here on the left-hand side with mics. And if you have a question, just give a hand and you will get the microphone. The first speaker is Professor Avila. Professor Avila, although we have the in brackets always made in Germany, has a background as Spanish. He is the Executive Director of the Center of Applied Space Technology and Microgravity in Bremen since 1.5 years, I think so, yes. And by the way, Sam is the organizer for the next ISC in Bremen and has a lot of work to do. And he has a MSc, Master of Science in Mathematics and PhD in Physics. But to hear more of him, just the floor is yours.
Yeah, thank you very much for the introduction. I'm going to speak about pushing the boundaries of research from our own perspective. And our perspective is highly influenced, as you can imagine, from our drop tower, which you can see there. It's 150 meters tall, and from them we can do microgravity experiments. Now, before I start speaking about what we do and about our research, I'll just say a couple of words about organization. So the drop tower allows us to perform nearly 10 seconds of experiments. It can be used by everybody in Germany through the DLR, or Europe through ESA, or everybody in the world if you contact us. And you can do an experiment you like and drop anything you like except humans. So it's quite a nice technology. What is our mission? What do we do there? We develop the space technologies of the future, and at the same time we use these technologies to test science, and more specifically fundamental physics. Then, as we are a university institute, one of our focal points also is to educate engineers for the emerging challenges of tomorrow. And I'll say a couple of things more about this later. Now, looking at our research, I'm going to focus today mainly on research that we performed under space conditions or microgravity conditions. And we work on fundamental science, very fundamental questions like the physics of cold atoms, Bose-Einstein Condensers, down to combustion for the rockets of the future, fluid management, for example, for the space station, or also for the cryogenic upper stages of rockets, down to quite applied fields like the development of energy-efficient materials for the cell phones of the future, for the displays. Now, saying about the drop tower, so all these topics of research are studied in the drop tower and other facilities. And sometimes we use the drop tower as a standalone platform for science, so we can complete all these projects, get publications and patents out of it just by using the drop tower. And also drop tower, and by many of our customers and by ourselves, can be used also for test bed if you want to later do parabolic flights, sounding rockets, or long-term experiments at the ISS. So just one example, I've talked now about fundamental science and applications, but even in the most fundamental case, these Bose-Einstein Condensers, there is a huge drive to improve technology just to do better fundamental science. So you can see here, in the first picture on the left, that's a typical Bose-Einstein Condenser laboratory. It would be a full room. In this laboratory from Kettle and MIT, Bose-Einstein condensers were generated for the first time. There was a Nobel Prize for it. Then you can see from a few years later, there was our first experiments in the drop tower, Quantus 1, so size of a human, nearly 4 seconds, much longer time. Then later, catapult, so up to 9 seconds, experiment gets smaller. And in the beginning of this year, the experiments were performed on a sounding rocket, and you'll hear more about this later by Jens Grosse. But the point here for technology is that through these steps, then lasers, very complex lasers, get miniaturized, smaller and smaller and smaller, lighter, more compact, higher performance, and it is important, for example, for later applications in satellites. And I'm not going to say more about applications because this comes later. So one thing about science that we want to talk about today is international cooperation. I think we need international cooperation from the very beginning, that scientists just meet together and talk about what to do. One example of this is cooperation with the US, with NASA. We're now in Becal, so that's a laboratory for cold atom research that will be going to the ISS in 2021. There's a cooperation for hardware and software between then DLR and NASA, and there is for the software as well as for the science. Other projects that we work with is the security or the safety of astronautical flights. You don't want to have a fire inside the space station or in a rocket, but what happens if you do have one? These are the type of questions we study together with USA, Japan, and Russia. And then also, together with Japan, we investigate ignition. Here we can see a visit of Mr. Okumura, so the president of JAXA, when he visited us last year. And then also with friends, I have an example here, fundamental science, where we test a principle of equivalence in physics. Now, my last point, and not the least one, because that's really important for us, is the educating our future engineers for the challenges that are emerging. And there we have several programs by which German engineers from our university or other universities throughout Germany and the world can do experiments. One of them, also funded by the DLR, is Rexus. So the students at the university develop a concept for experiment, They implement it and then fly it in a sounding rocket. Here you can see to the right our experiment of the University of Bremen, where our students were testing the propagation of fire. Then to educate engineers, so we have the lectures, but you also want to get them very excited about space technology as you compete with other fields. And that we were pleased when Robert Lightfoot last year gave a talk for us at the University of Bremen, because this had really a long-term impact for our engineering students, convinced they will go for space engineering now. And then, of course, besides the courses I said, we make an effort so that students can, for example, plan, design, build, and fly their own rocket. You have an example here from the program STEM. And of course, you can not start early enough. That's why we also emphasize that high school students come to us and also build their experiments with our own. And this way, we also get more females interested in these topics. Yeah, so with this, I would like to conclude, and I'll be happy to discuss questions later. Thank you.
Yeah, thank you very much, Professor Avila. The next speaker on our panel is Dr. Stefan Ola Metz, also with a non-German background, Austrian, but he is studied in the University of Graz. He's a physicist and made his PhD grade in Graz as well. He had an intermediate step to ESA, and since almost 25 years he is at DLR, and for us he is something like the face of Rosetta. He was mission manager for Philae, the lander, and at the moment he is responsible for the mascot, or the payload manager for mascot. Okay, the floor is yours.
Okay. Thank you very much, and good morning, everybody. So, indeed, I will give you a few words and insights on what science can do for society, what's the use of science, of course, for obvious reasons, in context with the Rosetta mission. So just to remind you, Rosetta has been one example really of European, I have to say, excellence throughout the world. It was a mission recognized all over the world, where we were able to fascinate people, also general public, with a scientific mission. It is an ESA mission, however, with a very strong German participation. The prime contractor was in Germany, and there was also a number of instruments, PI-led on the orbiter from German institutes. I've listed it here: OSIRIS, the camera, but also COSIMA, RPC, and the radio science instrument. And there was, of course, also the lander, Philae, a contribution to the ESA mission, again by an international consortium, but under DLR lead. Talking about scientific missions and the importance, I think besides of possible spin-off for economy or spin-off you get for future technology, there is also the cultural aspect. And I've given you here a few examples of early images of comets from the tapestry of Bayeux. You see here very, in the bottom left, a very old silk drawings from China from about 300 before Christ, and another image of Halley's comet from a manuscript in 1513. So these comets were fascinating people. People did not understand what it was, but it had a cultural aspect, a bit similar maybe as the moon, which we see every day, and also ancient people saw it, which rose mysteries, fairy tales, travel to the moon. Comets have a little bit a similar effect, and we should not forget it, this cultural effect which basic research is also covering. Now, the Rosetta mission itself, again, just a few key parameters to remind you. An ESA cornerstone mission in the science program was launched in 2004. Then we had a 10 years cruise until we arrived finally in 2014 at the comet. The whole story built up. We only in 2014, when we arrived at the comet, were able to characterize it, to find a landing area in November, eventually to deliver Philae to the surface, going with Philae and Rosetta and the comet closer to the sun, seeing how the comet went active, and the mission went to an end in September last year, when also the mother spacecraft crashed on the cometary surface in a planned manner. Operations, I'm talking here about panel of what's the German contribution, so I'm emphasizing on the control centers in Germany. Of course, Rosetta, the mission control center was in Darmstadt, the ESA center, but also the lander control center was in Germany, in Cologne, in DLR at Musk. There was also control centers in Toulouse and in Madrid from ESA side. Here, just to show you a little bit the fascination of this mission, a wonderful image where you see the comet with the shape which completely surprised us, as you probably know, and a wonderful jet here where you see how the comet gets active, how this tail of the comet is built, and that's another image taken by the OSIRIS camera from Max Planck Institute as prime contractor of surface areas on the comet. This roundish thing you see here, by the way, that's not the crater, that's built by the activity of the comet. That's really where the jets go out, where the landslides fall into this pot, and where the dust and the gas is ejected. The Philae lander, also here a few examples. Obviously, I'm not going into detail, but you see some images of the Rollies camera looking down during the first touchdown, and the other image was taken by the Shiva camera. That's the final landing site where you see really, like an astronaut would see it looking out of the window, the surrounding of the cometary material which is really 4.6 billion years old, just to remind you. That's the oldest stuff in our solar system. Talking about the fascination of Rosetta, the fascination of Philae, of course there was also a story behind. The landing did not work just as it should, but we found the lander again. Eventually we could get wonderful scientific data, and the story went on. The big thing which was left for Philae was to find it, to see Philae on an image from the orbiter. And if you look very carefully on this picture, you see Philae where we found it just a few days before the end of the mission. And if you have good eyes and you look here, you see the lander as we parked it in the garage on the surface of the comet, in a very shady place, unfortunately, but still in a position which allowed us to do plenty of science. So to summarize, Philae, Rosetta, just an example I wanted to give for science and the effect of science on society, on economy, on technology. A very important aspect, particularly of the Rosetta mission, was the fascination, the worldwide fascination we could deliver, the encouragement, as I'm sure we did, to young people to getting involved and getting interested in science, in technology. And of course, the Rosetta mission will be a benchmark for every future mission to small bodies and comets in particular. Thank you.
Thank you, Dr. Ola Metz. Let me introduce to you the third speaker. It's Matthias Mozzi-Gemba from the TSAT company in Backnang, Germany. He started as a young telecom engineer in different companies in Germany. Some of them are well known, like Siemens, Bosch, and A&T. And since a long time, he is with TSAT, and there he's responsible for sales and more or less sales activities. And we will hear something from him about TSAT and new products, high-tech products. Thank you very much.
So, hello everybody. TSAT Spacecom is a company. You might think, okay, what do we do here in terms of a panel regarding science. So all my colleagues are in the real fundamental research. But TESAT is a good example to show what we have in Germany, especially the title of the panel, to push boundaries, and a use case or a best practice. What we do in Germany is that we have a very good relationship with a fundamental research, what is needed to push the boundaries. And on the other side, a handshake which gives us the possibility to place some questions, fundamental questions, which lead us then to a next step in terms of a product. So for us, everything starts with a vision or with a concept. Before you go in science, you would like to know what could be a next step, and of course, not to forget that everything what you are doing have to have a benefit for the society. And 20 years ago, we started exactly with that, to have a question regarding what is needed, yeah, for the future, and everything is based on a good communication infrastructure. So, like the internet today is a disruptive technology. Everything starts with internet, but an internet would never have this high performance if you would have a fiber network on the Earth. And what we are doing is to lay the fiber in space. So the benefit for the society is to offer a high performant and a resilient communication infrastructure in space. And the resiliency is given by the use of optical inter-satellite link. Between these geos, what you see here, we lay these fiber based on lasercom between geos, so 80,000 kilometers between these spacecrafts, 1.8 gigabit, which is quite nice. So even on Earth, some of the colleagues do not have that in their household. So based on that, 20 years ago, more or less, it fits to the day of this event. In 1997, there was also a dream or a vision from someone. At this time, the name, it was Teledesic. Motorola was an investor, and they had this dream of giving a very good broadband service with high connection, which need then 840 spacecrafts. So today we discuss again mega constellations, LEO mega constellations, and 20 years ago this dream or this vision was given. And we took that challenge in Germany, and then here all these success stories starts at this time, because given by the government, the German Space Agency, together with Deutsches Zentrum für Luft- und Raumfahrt, DLR, and the Institute of Communication and Navigation in Oberpfaffenhofen, we started to go for this challenge. So it was at the beginning of fundamental research. In the end, after all that, we ended up with a lot of products, so spin-off products. So the first step was in 2007 that we also here in an international research cooperation with United States, we proved the first concept in terms of pointing, acquisition, and tracking. So the putting out of your science mission to say, okay, what is the most challenging thing to solve? And it is exactly that you have to target two first-moving LEOs, 25,000 kilometers each, in different directions, Doppler shifts, and all these nice things you have, and then to point to each other, to track each other, and to start communication with 5.6 gigabit. And that within 20 seconds. That's a mission. That was a challenge, and we did it. And why we were so successful? Because we had this close cooperation with fundamental research. So Fraunhofer Institute, universities, different institutes from DLR, Ferdinand Braun. So I have more than this here on the list, that we asked questions and we got responses. And based on that, we then went to the next step in 2013. We had then the first goal to have a GEO position, so 45,000 kilometers, so a long-range version, which gives a service to the Copernicus, to the European GMES, or now Copernicus program. You might know that we have the Sentinels flying, and that's now giving us also the benefit for the society that we can deliver all the sensor data from the Sentinels through a laser link, through the Mission Operations Center within minutes. So the people do not have now to wait any longer. So if you have a disaster, you can handle all these data within minutes, and giving back now. First, you got something from the government in terms of fostering technologies, but at the end you can pay something back if you have then new services which were not known before. Next step, of course, is miniaturization. We have to go smaller, LEO Smart version, and at the end now there is now a market. Again, there is a lot of requests outside regarding constellation terminals, and today we can. It's not that we used all these intermediate steps to deliver, and at the end now we also can have a solution for that constellations. We are celebrating this year 10 years Lasercom in orbit. So the fiber network in space built by TESAT is what you see here. So we have two geo positions. We have AlphaSat, we have EDRSA. These are the data relay nodes. We have the flying customers, the Sentinel fleet, 1A, 2A, 1B, 2B. We have ground networks. We have a ground station in Tenerife Island. And there is also a very good example that we have now this infrastructure of laser communication from ground to space between the aircrafts, between spacecrafts. Aircrafts are now entering in that market. And this is now a perfect testbed where science can work on. So next steps are quantum key distribution via Lasercom. Yeah, in Tenerife Island, we have a test bed, and I guess, speaking without your control, to say you are highly invited to use that test bed for fundamental research on Lasercom, on photonics, on quantum key distribution. That are a perfect setup to use. So what you see now, meanwhile, because based on a commercial orientated company, we have now products. So products for different markets. So we have data relay market. There is geo Lasercom terminal, so the resilient backbone. We have a smart version, so to be more affordable on smaller satellites with Lasercom terminals. We have direct to Earth, not to forget that. We have different wavelengths, 1064, 1550. We do not care about wavelengths because we use the media which is made for, which is the best for. So long range 1064, short range 1550. The airborne market is coming, beyond line of sight connectivity, and now the constellation market. So to summarize, we are standing for this partnership, of course, science, handshake, what I see between fundamental research, but orientated also in a commercial use. And then do not forget the applications on it. But at the end, it must have a sense, application. Application level is needed. On all your smartphones, you're using the application, not the frequency for anything. So now we can deliver space-based internet, yeah, which is, I think, a good thing also for 5G, for the next steps of high-moving data. Quantum key distribution I mentioned, so don't forget that everything must have a benefit for the society. Thank you.
Yeah, the speaker number 4 is Dr. Jens Große. He is an aerospace engineer, and now he's a system engineer at the University of Bremen, and they're, among others, responsible for the backup payload for the ISS and cold atom letter. So the floor is yours.
Thank you. and welcome to all of you. I'm here today on behalf of the Quantus Consortium, and I would like to talk about our Quantus projects and about bringing cold atoms and Bose-Einstein condensates to space. So first of all, I want to answer the three most frequently asked questions. What is the Bose-Einstein condensate? How do you do it? And what can you do with it? So a Bose-Einstein condensate is basically about bringing atoms to a cloud of atoms to a very cold temperature in the nanokelvin range. So they are really slow, and then they start behaving like a wave instead of single particles. So how do you do this? Basically, this is about what you can see on the lower left-hand side. This is a vacuum chamber with telescopes and a lot of coils attached. So you use magnetic fields and laser light to cool down the atoms in an ultra-high vacuum environment. And these Bose-Einstein condensates can then be used to perform atom interferometry. And this is used to measure, for example, accelerations. And yeah, these experiments or these measurements are the sensitivity scales with the time of free expansion. So this means you're basically limited by the size of your vacuum chamber if you are on ground. So this is where space comes into place. So if you go into a microgravity environment, you have the opportunity to perform experiments with a long time of free expansion and therefore do high precision measurements. So what is this all about? What can you do with it? You can use it to measure the gravitational field of the Earth very precisely. This means it could be used as a next generation gradiometer for Earth observation. So studying tidal phenomena and understanding the climate on Earth, for example. You can do high precision measurement in inertial sensing, so measurement of accelerations, as I already said, and rotations, of course. And this is what we are into. We are doing fundamental physics research, and the topic we are focusing on is testing Einstein's general relativity theory. So in our project, we have basically three columns. So the one is the drop tower. Then we are also carrying out experiments on sounding rockets. And last and very recent, we started looking into experiments on the International Space Station. So as you can see on the timeline, there are a lot of firsts in there. In 2007, we succeeded in having the first Bose-Einstein condensate in the drop tower in Bremen. So this was a huge milestone. And I want to talk about, no, this is not working, about our most recent milestone in January this year. Our research team went to Sweden, and there on the right-hand side you can see the payload team in front of the payload in S-range in the north of Sweden. Then you can see our control center and the launch of the first Marius rocket on a VSB-30 sounding rocket. And there we succeeded in doing the first BEC in space, actually. But this is not only about the fundamental physics, this is also, the fundamental physics is a technology driver, so we developed in our project a lot of technology. We are talking about atom chips, so tiny planar structures where you can generate magnetic fields with. We are talking about micro-integrated laser modules, we're having vacuum technology, and very compact electronics, as you can see in the pictures. And this is also about learning how to do Bose-Einstein condensates in microgravity. So we have the experimental techniques and the expertise of performing these experiments in microgravity. And this results, of course, in some highly ranked publications, as, for example, here, this publication in Science that was released in, I guess, 2009. And of course, as Mr. Avila also said, it's all about education. So we are offering students, not only bachelor and master students, but also, or foremost, PhD students, the opportunity to have a hands-on experience on those projects and on that technology. So this is what it is also about. And then I want to talk about the international aspect. We have most recently some activity ongoing to bringing those cold atom experiments onto the International Space Station. There is a cold atom laboratory currently prepared for launch and will start hopefully February 2018. And our consortium is proposing experiments for this facility that is built and brought up by NASA. And we are already in the planning for the next generation cold atoms facility called BECAL, and Mr. Avila also mentioned it. This is a cooperation between NASA and DLR, so NASA is using German technology and expertise and the Qantas and Maya to actually build the next generation cold atoms facility on the ISS. And the status is that we are currently in the design phase, and we hopefully have this CDR in end 2018, so end next year, and the launch in 2021. And with that, I want to conclude. So we have the Quantus Consortium looking into BoseEinstein Condensers in microgravity. It's a research funded by the German Space Administration. The project was started 2004. We have a collaboration of 11 institutes from Germany in international cooperation with NASA, and I guess this is a good example for international science made in Germany, and that's what the panel is about. Thank you.
Yeah, thank you very much to all of you. And thank you very much that you always kindly mentioned the support of the Space Administration of my team in Bonn. It gives me the idea that we invested in the right technologies. Yeah, thank you very much. We have something like 50 minutes left. Now you in the audience have the chance to ask questions. Is there somebody who wants to dares to ask the first question? Oh, really silence here? Okay. Then let me ask a question. Mr. Ola Metz, you spoke about fascination and young people and inspiration, but what you have done gives this also inspiration to people who have to develop products. Can you give an example for this?
Yes, I can, but one has, of course, to see Rosetta really is basic research, so the application is not obvious. And still we have, I showed you the image of the Rolle's camera where you saw the comet getting closer and closer during landing. A derivative of exactly this camera, the Rolle's camera, is now used for forest fire protection. So that's a direct spin-off which really serves society and which is a product which came from a development done for a cometary mission. Yeah.
So there's a direct link from basic science to products. Yeah. You are on the one end, far end of the value chain. Mr. Motsi-Gemba is in the other end of the value chain. How important for you is this type of basic research? And the second question is, you mentioned several technologies, several research partners, like Fraunhofer and DLR. How do you manage to bring these different technologies and scientists together to develop from their ideas a product?
Yeah, it's also very challenging sometimes because of course what is needed is to sometimes to make from a one-off to bring this then to a sustainable production. Yeah. In this example nowadays when you have a constellation and you have to deliver 1,000 terminals, yeah, in 3 years, yeah, you need that repeatability of results. So first is that of course is close cooperation to give questions, yeah, and to have a very deep knowledge what is ongoing, yeah, in terms of what could be a next step in terms of our product evolution. Yeah, for example, now integrated photonics, that's a very hot topic, where we then go to these institutes and universities and ask, do you think, is this available? Can we do that in another way? Also to have workshops together with them. Ask questions, yeah, and then also a helpful thing is within ESA that we have different maturity steps in terms of fundamental research, of R&D, of different programs, artist programs, and so on. All these things are very helpful.
Yeah.
I would like to say something more about this, because mainly we are focusing here so far on saying we have this technology, and then with this technology we can test this science, or what is the technology we need to test this science. And I think there's another aspect which, especially in Germany, we can learn a lot from mechanical and chemical engineering, where the universities and the companies cooperate much more closely on the development of technology itself. I think that's a point where in space engineering we can learn from other fields, not only about the scientific missions and how to use the technology for scientific missions, but for the development of the technology itself.
Yeah, thank you. Question to you, Mr. Grosse, and you, Professor Avila, you mentioned quantum technologies and these. When do you think will they arrive as products on the markets? Good question, eh?
Yeah, this is difficult to answer because, as I said, we are currently focusing on fundamental physics, so there's no direct application for that. However, if you consider what I said earlier, that there is an application in Earth observation, it's just a matter of time that you say, okay, you need more precise measurements of Earth's gravitational field, and that you want to have a deeper look in that, and then there might be this application, and there might also be a market for that.
Okay.
But at least to measure gravitational fields, and that has a lot of applications, the technology is not so far from the market, right?
Yeah, that's true. So our technology is pretty mature right now, so we have developed a lot of technology for that, and so you could basically use that, and yeah, with at least not so much effort, put it on a satellite. This should be possible.
Professor Avila, in your activities, microgravity is in the core. Yeah? How important is microgravity if you look to future markets?
So if I think about future markets, and then probably I focus now in the example of material science. The example, if I take, unfortunately this here is water without gas. It's not sparkling water like the one we usually drink in Germany. But if this were sparkling water, you would see now the bubbles rising up. If you are under microgravity conditions, then bubbles don't rise. The buoyancy forces are not there. And then, for example, in material sciences, we can use this property that heavier materials are not then heavier under microgravity than lighter materials, and this can help us develop very, very precise, very uniform crystals. And I think there's a market there for the generation of materials. I mentioned before the displays of computers or of cell phones, but also there's in glass fibers and there's a potential, I think, to reach the market in the near future.
Okay. Yeah, thank you very much. Again, back to the audience. Is there somebody who wants to ask a question? No? Yeah, bitte. Here in the front row.
G'day, I'm an aeronautical engineering student here at the University of Adelaide. I'd just like to know, to what extent do you guys bear in mind that transition between, I suppose, the drivers behind the fundamental research and the offshoot into products and into the industry? Do you attempt to somewhat bear that in mind, how you might be able to guide that within your papers, or is it more just you leave it to the universities and the I suppose, the institutions that actually kind of fulfill that niche themselves?
Thank you. Good question. Who wants to give the first answer?
I can give an example related to the propulsion of rockets or upper stages, and then we read the papers that our colleagues from Airbus publish, and we, or Ariane Group now, we read these papers, they read our papers, and there's definitely close collaboration where there's a direct benefit of our research for them. So it depends very much on what application, but in many fields we are really closely working with industry.
Dr. Grosse, if you think about the question of the colleague, have you in mind when you are doing your daily business, what could be done with this in products and markets? Or it's you're too busy with your science work?
Yeah, it's definitely a lot of work, but as an engineer, I'm already focused on, might there be application, might there be a market? So I try to address that at least in an outlook always, so that you can really have that in mind. I guess this is something that I could just encourage everyone to, because in the end, otherwise it just gets lost what you have done somehow after years.
Okay.
Yeah. So a normal day in the life of a product manager is that you see your boundaries. Yeah, boundaries. So it comes that you have a product, yeah, and it comes to a customer market, and most of the time, this product does not fit. So we have now 10 gigabit, and you ask, oh, you might have something in 40 gigabit or very high throughput feeder links. So the most challenging thing for Lasercom is go to the atmosphere, and there is a huge market outside. In terms of the customer operators, which says, okay, we need an optical uplink in terabit per seconds. So now you have the atmosphere, you need another coding, you need modeling of the atmosphere, you need the full communication chain to handle that, you need processors on the spacecrafts to handle terabytes, terabit, and the whole flow. Out of that product, now you have a lot of questions and not existing technologies. And therefore, it might be a good thing then to have in mind a technology roadmap, and to share this technology roadmap. So someone have to have a system architect in mind. Of course, that's maybe some secret, but then to put it in a technology roadmap to say, okay, here we need a fast-speed FPGA. So who takes care about that? And then to share these puzzle parts with the community, to push these boundaries to the next step.
Okay. Was this a good answer for your question? Yeah. Okay, thank you. Is there another question from the audience? No, not anymore. Then maybe I would like we have 3 minutes left for one last question. How important is for you the international cooperation? Maybe.
Well, if you're talking about big space projects, space research, flying to a comet, I could give many other examples. International cooperation is, of course, essential. And it becomes more and more important the more spacefaring nations get involved. We've learned Australia is going to have a space agency soon, so that will certainly be another partner to get involved. We do space science, we're a science community. So it is important not just for doing the science itself, but also to give the impetus and the push to go for such missions, to have a wide international community behind it. On the other hand, it's also not difficult to get this engagement, since it's fascinating missions. And honestly, I do not see, we never really had problems in fascinating wide international communities and engage them for cooperations.
Yeah, I would add just something very brief, which is I like cooperation. I think it's necessary just because our personal and cultural background influences very much how we see science. And I cannot imagine doing our work without the perspective from our international colleagues. It just wouldn't work.
Mr. Mozigema, the international network of the scientists, is this a help for you when you think about tapping into the markets?
Yes, exactly, because it inspires. It's every time it's inspiring. We are in a such, for us, small world. Yeah, so we have a key or an on-the-edge technology with laser communication, and without the full exchange between all science members in the world, yeah, we wouldn't have reached that goal. So it's fundamental that researchers working closely together, and that we have access to that technology at the end. That's very important.
Okay, thank you very much. Please give a small applause to the panelists. We made a broad view from the basic research to innovation and application, a little bit about made in Germany, and I personally think that the important input from science is that they push the boundaries, and these new areas developed by science, these are the fields where innovation and new products grow. Okay, thank you again for joining us. Thank you very much. Bye.